So now we have the mass of a drop. We have the velocity. We have, therefore, the momentum of the drop. What's left? How many drops are coming in a certain time, right? So in order to figure that out, well, what's the strategy? Doesn't fall like solid water, fortunately.
1 meter cubed.
That's called a waterfall, not a rainstorm. So what do you think is the typical distance between drops?
Half a meter?
Half a meter?
I guess it depends on the
That's
severity.
very optimistic.
We need a lot of rain. How about 10 centimeters?
Okay.
All right. So the distance between drops, so drop to drop is about 10 centimeters, let's say. Okay, and these drops are on a cubic grid so that they make our lives easier. Okay, so I need to figure out how much momentum in a certain amount of time. So all these drops, if I draw an imaginary box, and the height of the box is the terminal velocity times some time interval, v delta t. Any raindrop in that box will hit the ground within the time delta t. You agree with that? And anything that's above won't have made it down far enough to hit the ground. So I need to add up the momentum of the drops in that box, which has maybe some cross-sectional area A on the ground. Okay, so the volume of the box would be whatever that area A is times V times delta T. But I need to know, apparently, the number of drops in there. How am I going to get that? So should I divide the volume by the volume per drop? What's the volume per drop? Each drop is about 10 centimeters from its neighbor. So each drop occupies a volume of about 10 centimeters to be cubed, right? So each one gets its own cube that's 10 centimeters on a side. They are, okay. And so the number of drops in that volume should be the volume divided by d drop to drop cubed. Because that's the volume per drop, the volume occupied by each drop. So that's AV delta t over d cubed. I'm going to stop writing all that horrid subscript, but it's the same thing. Okay? So that's the number. The momentum now is what? So delta P would be the number times the momentum per drop, or the mass times the velocity, right? So that would be the number of drops times, what did we get? We got the mass of a drop times V. So that's the momentum per drop. That's the number of drops. So let me put it all together with this expression for n. So we have AV delta t d cubed m drop v. So it looks like we have two powers of v that come in there. Okay? So that's delta p. So what about the average force? Yeah, divide both sides by delta t. The average force will be delta p over delta t. So that's a v squared over d cubed m drop. And what would be the average pressure? The force per unit area on the ground. Yeah, I just get to divide out the area. So the average pressure would be the force over the area. So that's even simpler. That's v squared over d cubed times m drop. So let's see what we get. We had v was, so p bar should be about 10 meters per second. Divided by, let's see, 10 centimeters is 0.1 meters. 0.1 meters to be cubed, and then the mass of a drop. Can I leave this in grams, or should I convert it to kilograms? I think I better convert in order to get the SI unit for pressure, because I've got meters and meters. So what would that be in 3.2 times 10 to the what in kilograms? Negative, it would be negative 3.2, negative 2 in grams, so negative 5 in kilograms. Okay, so that's 100, that's 10 to the 5. Oh, isn't that convenient? So isn't this 3.2? And then I need to work the units, so I have meters squared over meters cubed, so that's 1 over meters. I have 2 seconds in the bottom, and I have kilograms on the top, which is a strange-looking unit, except that if I were to multiply on top by meters and then square on the bottom, kilogram meter per second squared is a what? A newton. So this is the same thing as 3 newtons per square meter, which is the same thing as 3 pascals. Pascal is just a newton per square meter. That's the SI unit for pressure. I'd like to compare this to atmospheric pressure. Anyone happen to know what the air is pressing down on you with? 100,000 pascals. So P atmosphere so you probably will not be terribly harmed in this rainstorm. Yes, right. So out you go. Okay, any questions? So we can use our idea about momentum to get an estimate, and basically we can make up some stuff. Are we going to be exactly right? No. How far off do you think we are going to be?
I don't know.
More than a factor 10? I don't think so.